Hello, and welcome to a lecture on geoanalysis of axisymmetric paraboloidal reflectors. I'm Steve Ellingson. Here's an overview of this lecture. What we're doing here is a first pass at understanding radiation from paraboloidal reflectors, and really paraboloidal reflectors whether they're axisymmetric or not. And we'll be doing this using geometrical optics, or GO. By doing this, we're going to learn a few useful things that will be generally applicable. And we'll also learn that we really need a method other than GO to get useful answers in this problem. So even though GO will turn out to be not an entirely satisfactory tool to use in this case, there will be some results which we will need and which we will find useful in subsequent work. In this lecture, we'll work through the construction of the GO solution, interpretation of the GO solution. We'll consider the polarization properties of the reflected field as revealed by the GO solution. And then we'll summarize and we'll describe the path forward in terms of analyzing paraboloidal reflectors. Okay, we start with an incident field. And for this we need a feed model. The idea is the incident field, E super I, at a point of reflection, Q, is given by some constant magnitude and phase, a unit vector which describes polarization, and that unit vector is parameterized in terms of the feed coordinate system. So let me remind you how that works. What we said is we would have a paraboloid that looks like this in cross-section, a coordinate system which looks like this. This is rho, this is z, this is the origin which corresponds to the focal point. And then we said we would have also a feed coordinate system, z sub f, and then also rho sub f, and so on. So the idea was that we have these two coordinate systems really for notational convenience. Similarly, we have the normalized pattern of the feed parameterized in the feed coordinate system. And then, as usual, we describe the far field pattern of the feed as a spherical wave. So, a very simple but general feed model, arbitrary pattern polarization, spherical wavefront. So those are the key ideas. Now we know in GO, the reflected GO field, as a function of distance along path length, that would be distance from Q, is given by the reflected field at Q times the spread factor times the phase factor accounting for phase accrued by propagation along the reflected ray. It's propagating in some direction, S hat super R, which is determined by the law of reflection, which you can also think of as being Snell's law. The wavefront curvatures in general are given by this expression, which we discussed in a previous lecture. This expression applies because we have assumed a feed which is creating spherical wavefronts in the far field. So we have spherical wavefront curvature at the point of incidence on the reflector. Just to remind you, S super I is the distance from the feed. Theta super I is the angle of incidence. R sub 1 and R sub 2 are the principal radii of curvature of the reflecting surface at the point of reflection. And then theta 1 and theta 2 are angles relative to the normal that describe those principal planes. It will turn out, as it often turns out, that we don't really need this full expression, but just to be complete here, we'll include it. And then finally we need the reflected field at the point of reflection. So here's the reflected field at the point of reflection. It's based on the incident field at the point of reflection. We decompose it into the TE and TM components, those being associated with unit vectors, which we described how to find in a previous lecture, and then the associated reflection coefficients, either plus or minus 1, assuming we have a perfectly conducting surface. Right? If we did not have a perfectly conducting surface, those reflection coefficients would become more complicated, but that's really all that would change. So now let's start to work this out. The reflected field at Q, given by the expression I just discussed. If we substitute the incident field at the point of reflection, again given by the feed model, and we make that substitution, we can rewrite the expression this way. The reflected field at the point of reflection is E sub naught, a polarization vector, E super R, the feed pattern associated with the point of reflection, and then the phase and magnitude of the incident field at the point of reflection, where the reflected polarization vector is given as discussed on the previous slide. This polarization is potentially complicated for reflection from a paraboloidal reflector, and it's potentially complicated even if the feed pattern is simple. So we're going to come back to this later. Next, let's consider the direction of the reflected ray. The very simple way to compute the direction of the reflected ray is shown in this picture. Here is some reflecting surface. Here is the point of reflection. Here is a unit vector describing the direction of incidence. Here is a normal to the surface. A very simple way to figure out which direction the reflection is going to propagate in is to identify the part of the direction of incidence that is in the direction indicated by the surface normal, and that's this dot product here. And then you want to remove all of that, and then remove an equal amount, which turns the ray around and sends it in the right direction. Right? So what we're doing here is we're identifying how much of the incident ray's unit vector is in the same direction as n hat, and then we're removing twice that, which turns the ray around in a direction which is determined by the unit vector. There's a number of ways you can confirm that this is right. You could try some special cases. For example, what happens if S super I is equal to minus n hat? You will discover you get the right answer. You'll also discover you get the right answer if S super I is perpendicular to n hat. Now we need n hat. So here's a general way to compute n hat. The idea is that we have some function that describes the surface. So S is a parametric expression for the surface. And we'll say how to come up with that in a moment. If you have this parametric expression, you can take the gradient of that expression, and that points in the direction of the surface normal. In particular, it points towards the direction in which the surface is concave. You want a unit vector, so then you want to divide this by the magnitude of that quantity, and that gives you the unit vector pointing in. And then, of course, you either want the plus or minus sign, depending on whether you actually wanted the normal pointing in or whether you want the normal pointing out. In this case, we want the normal pointing in for a reflector antenna problem because the feed is on the inside, it's on the concave side, so we choose the plus sign. So we can compute the surface normal as plus the gradient of the surface function divided by the magnitude of the gradient of the surface function. So what is S? It's a parametric description of the surface, and it has the form that this function is equal to 0. Now this is a concept that comes from differential geometry, and it's relatively simple, but I realize most students typically are not exposed to this before taking this course. No worries, I'll kind of walk you through how it works in this application. We derived in a previous lecture that for a paraboloid, the distance from the origin to the point of reflection, that's r sub f, is equal to f times secant squared theta sub f divided by 2. So just to draw the picture here, here's the reflector, here's rho sub f, Here's z sub f. This is a ray incident. This is a ray reflected. So this distance here is r sub f, the distance from the feed, which is at the focus, which is at the origin, to the point of reflection q, right? And then this angle is theta sub f. So now I can solve this expression for f, the focal distance, that's r sub f divided by secant squared, theta sub f divided by 2. And I can rewrite this as r sub f cosine squared, theta sub f divided by 2. Now I want something which gives me 0, as I indicated on the previous slide. So I simply subtract the right-hand side from both sides, and I get f minus r sub f cosine squared, theta sub f divided by 2 equals 0. So that's going to be our parametric description of the surface. Specifically, we have some function s, which is equal to 0 always, and it's parameterized in terms of the geometry in the feed coordinate system. And the function turns out to be f minus r sub f cosine squared, theta sub f divided by 2. Okay, so here I am rewriting the expression from the previous slide. I take the gradient. Now I'm obviously in a spherical coordinate system. So I use the gradient in spherical coordinates. The gradient is given in terms of the 3 unit vectors in the spherical coordinate system that's relevant here. R, theta, and phi, all sub f. And then I take partials with respect to those coordinates and put them together as indicated in this equation. So what I find here, and you can do this very quickly, I won't walk you through it step by step, it's quite simple. You find that the gradient of s is minus r sub f, the unit vector, cosine squared, theta sub f divided by 2, and then you get a theta sub f component, which is equal to cosine theta sub f divided by 2, sine theta sub f divided by 2, and no phi sub f component, because the gradient in the phi sub f direction is 0. We only get an r hat and a theta hat component. So rewriting that expression at the top of the page here, the magnitude of that expression is simply the square root of the square of the components. So here I've written that. Here's the r sub f component. Here's the theta sub f component. And you can quickly work through this. Just simple math again. Magnitude of cosine theta sub f divided by 2. And since theta sub f is always less than or equal to pi, we end up with the fact that the magnitude of the gradient of the surface function is cosine theta sub f divided by 2. So now we're ready to come up with an expression for the surface normal. It is the gradient of the parameterized surface function divided by the magnitude of that thing, and we end up with minus r sub f cosine theta sub f divided by 2 plus theta sub f sine theta sub f divided by 2. So a relatively simple expression. And you can see now that there should be no phi sub f component because this surface normal to the paraboloid should never have a phi sub f component. You can probably visualize that quite simply. You can do some simple checks on this. It's always a good idea to try to do that. For example, in the special case in which theta sub f is equal to 0, the surface normal is minus z sub f. That is this case here. So if theta sub f is equal to 0, that's this direction along the z sub f axis, and at that point of reflection, the surface normal is back this way, in other words, in the minus z sub f direction. Okay, so now let's return to this issue of the direction of the reflected ray, since we now have an expression for the surface normal. We simply recognize first that the direction of incidence is equal to r sub f hat, so we make that substitution. And note that r sub f dot n hat is simply the r sub f component of n hat. And now we're just going to do a little bit of manipulation here. We've got an R sub f component over here, an R sub f component here. We can regroup this so that we have our expressions sorted by the different vector components in this coordinate system. So here's the R sub f component, and here's the theta sub f component. Here's that expression rewritten at the top of this slide. We can very quickly work through this. This looks just like and is a trig identity related to cosine theta sub f. This, in fact, is another trig identity related to sine theta sub f. So you can write down those expressions very quickly just by verifying that they are the trig identities that I've implied here. And in fact, if you look carefully at this expression, you quickly find that the direction of reflection simplifies to minus z sub f, which is plus z in the global coordinate system. In other words, it appears the direction of reflection is always this way. We have shown that every ray incident on the paraboloidal surface is reflected in the same direction, and we refer to this as collimation, which is obviously what we want for this kind of system. Okay, so now we're continuing to put together the geo-reflected field solution. We need the curvature of the reflected wave. Now we know in advance that the wavefront radii of curvature should be infinite, because we know this whole thing has been set up to create a plane wave in reflection. So we can substitute those known radii into the expression for the spread factor. You do this in the formal mathematical way, simply by taking the expression for the spread factor and letting rho sub 1r and rho sub 2r go to infinity. When you do that, you find the result is 1. And again, this should not be surprising. This is more verification than really derivation. Of course, the spread factor is 1 because there is no change in power density as we move along any reflected ray, right? A plane wave has no reduction in power density with increasing distance along the propagation direction. However, you should note that this simplicity is lost if the feed is not located at the origin. If we move the feed from the origin, which is, remember, also the focal point, then this whole thing would be much more complicated. Okay, the phase of the reflected wave, another component of the geo-reflected field solution. Well, we know that to get to any plane, we must traverse a distance equal to r sub f, right? This distance here, for example, is r sub f, right? And then this distance here would be written as s sub r. And for each of these rays, r sub f and s sub r is different, but the sum should be the same. All right, so in the phase factor, we get e to the minus jk r sub f s sub r for each one of these rays. These two distances should be different, but if this is a plane wave on reflection, the sum should be equal, right? And if it's equal for every ray, it's also equal for the ray which goes to the vertex and comes back out directly this way. And that distance is f plus z. So we can replace this with 2 times f plus z. And then we'll sort this out so that we've written it as the product of e to the minus jk2f. That's a constant because it depends only on the focal length, times e to the minus jkz, which is a more traditional looking phase factor. So now we put it all together. This is our general form. We've learned a whole bunch about what goes in here, so we can apply it. We know that E super R is this whole thing. We know the spread factor is 1. And we know the phase factor is e to the minus jk2f times e to the minus jkz. And then we can rearrange things here a little bit to make it a little bit more convenient to work with and easier to identify what's going on. We pull out the polarization vector, E super hat, which we have not yet worked out in detail. We only realized it was going to be complicated, so we pulled that out. Then we've got this thing, which is really talking about the field incident on the point of reflection due to the feed, right? E sub naught is associated with the feed. This is the feed pattern in that direction. This is a phase factor, which is this constant thing that we found here. We're just pulling this inside square brackets. R sub f, which is a distance from the feed to the point of reflection. And then just a plane wave phase factor, e to the minus jkz. Let me continue to work this a little bit more. And note that this is a non-uniform plane wave. This is a non-uniform plane wave because this thing here, which is the same as this thing here, is not constant magnitude. The magnitude here is going as 1 over r sub f. And r sub f is changing as a function of the point of reflection. Furthermore, the feed pattern magnitude is quite likely changing as a function of these variables. So we see that the reflected geofield is a plane wave to be sure, but is a non-uniform plane wave. Its magnitude varies as a function of where on the dish the point of reflection is. And then here I'm simply rewriting the expression that we know we must use to get the reflected field polarization.